So welcome everyone. It's good to be with all of you on this beautiful Good Friday from inside of our various COVID offices. I'm excited about today because we get to keep talking about triple integrals. I'm excited about today because we get to talk about some data analysis afterward for those that want to run a few of the numbers related to COVID. Very good. So let's dive in and keep talking about the triple integrals. The approach that I'm taking in this class is to say that in my experience, the difficulty with evaluating triple integrals isn't so much finding antiderivatives. That's just a lot of writing. You've been working on that for multiple quarters. The challenge with multiple integrals is in the setting up of the limits of integration. And so I'm planning on spending most of our time, once again, talking about setting up those limits of integration, because I think that that's where my experience will be the most beneficial to you. If you want more than that, of course, you can stop by for office hours or set up an appointment, and I'm happy to walk you through integrations themselves and kind of those reminders in that process. But let's spend our time kind of on the stuff that's probably the most challenging. So let's pick up where we left off, which was on example 4. And example 4 looks something like this. Looks something like this. So it says, consider the integral I from, so a triple integral from 0 to 4th root of pi, 0 to z, 1 to z, of 12y squared z cubed sine x to the 4th dx, dy, dz. There's a whole bunch there, but I want to point you to something right here at the outset that will probably remind you of something you faced back in Calc 3. So right here at the beginning, we're trying to find an integral of all of this garbage with respect to x. And when you go and try to find the antiderivative of this with respect to x, you'll notice you have this sine of an x to the 4th, and we don't know the antiderivative of sine of x to the 4th. We could probably use some of our Calc 3 skills and use a power series. So maybe we could write this as a Maclaurin series, and so you'll have like a triple integral of a infinite long polynomial with sigmas in there. I mean, we might be able to do that, but that sounds very challenging. And so in the face of that challenge, we want to take advantage of one of the powers of the multiple integrals, and that is that we have the freedom to change our order of integration, and sometimes that makes things a little bit easier. So what we're going to do is we're going to change the order of the limits of integration, and that's going to make it so we can start by integrating one of these y squareds or z cubes, which will be easy, and we hope that the sine stuff will kind of follow. We optimistically hope, and since it's a textbook, usually that kind of stuff works out. So does everybody understand why I might want to reorder this integral or reorder these limits of integration? Does that make sense? Okay. Very good. All right. Just watching for the thumbs ups. So the first step, if you want to change the order of integration or set up a multiple integral, is to sketch a picture. And this particular picture is kind of this triangular wedge type of object. Yesterday in class, Melissa asked a question about how you sketch 3D curves. And then after class, we continued on with this conversation. And I think it was Enrique asked me whether it was okay to use technology to graph these curves. The short answer is yes. Yes, if you want to use software to graph these objects, by all means, be my guest. Use all the tools at your disposal. So I think there's like if you're on a Windows box, you could use the Microsoft Mathematics software. There's lots of internet apps. You could use Wolfram Alpha. There's all kinds of things. In my experience, the challenge in graphing objects in 3D tends to be trying to find the boundaries, and so the objects tend to just sort of go on top of each other. So it'll still take you some cleverness, but by all means, feel free to use your technology. So in this particular case, we have this kind of triangle wedge-shaped object. I think I have a manipulate for it. So it looks something like this. Is a triangle on the top, kind of a wedge, pointy on the bottom. And what we're going to do is I just want to start by talking about where this graph comes from, like how you would find it. So if you wanted to find the graph, then you would look at the limits of integration that you were given. Doggone it. I cannot see them and the window at the same time. So our x values are going from 1 to z. So if you're traveling this direction, parallel to the x-axis, you'd be going from 1 to from x equals 1 to x equals z. If you're traveling parallel to the y-axis, you'd be going from y equals 0 to y equals z. And if you're traveling vertically, you'd go from z equals 0 to z equals 4th root of pi. You might say, hey, Dust, that's all fine and dandy. How do you how do you sketch that? And you might recall yesterday in class, that was where I showed you all those consecutive sketches that I'd done, where I just sort of sketched over and over and over again, trying to understand what it was that I was looking at. So the way the original graph is constructed, we integrate with respect to x, then y, then z. Think alphabetical order, x, then y, then z. And you can see this in the picture where we are starting with the green arrow, so integrating parallel to the x-axis. So here's your x-axis. So the green arrow is parallel to the x-axis, and you can see that it's entering in one curve, and it's coming out in another place. So that was the arrow that I kept talking about yesterday. It sort of enters the object here, goes through, and comes out below. And then we do the y's, so parallel to the y-axis. Sorry. So parallel to the y-axis, start at y equals 0, so it comes in here, comes out here. And then the z's are are starting down at the base and going to the top. But we want to reorder this integral. And so whereas we started with going from x, y, z, see if I can type some notes. Started dx, dy, dz. So we started dx, dy, dz. Now what we're going to do is we're going to try to do something else. We're going to try dy, then dx, then dz. So we started with x, y, z. Now we're going to try y, x, z, just a different order of integration. And so if we want to start with the y's, in order to start with the y's, just like we did in class yesterday, we focus in on the 3D drawing, and we take an arrow and we run it parallel to the y-axis. So here you are, parallel to that y-axis. It enters the object kind of on this back face and comes straight through and comes out on this front face. So it's going in at y equals 0, and it's coming out at whatever this surface is over here. I think this is y equals x. It's coming out at y equals x. Okay, let me pause. Questions so far? Very good. So once we've taken care of the dx, we've taken care of the y direction, then we can project this onto one of the 3 coordinate planes. So remember, I think we're trying dy, dx, dz. So we've already taken care of y, and so we could project onto one of the 3 coordinate planes. So notice, if we took this object and we projected it onto the YZ plane, we would get some sort of a triangle shape. If we projected it down, we would get this triangle on the XY plane. But what we're interested in is projecting onto the XZ plane, which would be right here. And as we did in class yesterday, we said, once you find that projection, then look at that middle variable and draw 3 arrows parallel to that axis. So our middle variable is x, so we're going to draw 3 arrows parallel to the x-axis. So 1, 2, 3. So our arrows are all going in at x equals 0, and then they're coming out at x equals z. Oh. The lowest, so that gives me my x limits, and to find my z limits here, we notice that the lowest arrow would be when z equals 0, and the highest arrow possible would be where z equals 4th root of pi. Questions?
I'm kind of curious, Dusty, because in the original iterated integral at the top, it had the limits of integration for x going from 1 to z instead of 0 to z. How did we shift?
From 1 to z, from 1 to z.
I think you should look up at the top of the
I think I got to scroll up. All my right here from 1 to z.
Or is that from y? Oh, I read that as a 1. My apologies. I see where it is now. That's a y to z.
Oh, snap. Yep. And I think when I said it, I said 1 as well. Yeah, that's a y.
Okay, all makes sense to me now. Thanks, Dusty.
Wow. May the rest of the course make that much sense that quickly as well. Cool. Sorry about the unclear scan there for everybody. All right. Other questions?
So you're basically just giving us like visual representations of how we found the limits, right?
Yeah. Yeah. When you go and you try to work these examples, you're going to find yourself saying the same thing that you've said over and over in math. Well, I can evaluate this when it's set up. The hard part is the setup. Anyone that's done math for more than about 5 minutes has said some variant of that. Like, it's, the hard part is the setup. The hard part is the setup. And after that, it's the crunchiness. And so I'm spending my time on the setup. And in this case, the challenge of the setup is in setting up the limits of integration. And because of the fact that this is a triple integral, setting up those limits of integration requires that you are able to work with something that's three-dimensional. You don't have to be a perfect artist, but you got to be able to have some sense of what's going on.
Okay.
Cool. Other questions?
Yeah. For your projections on each of the planes, how did we know that x equals z, y equals z, and x equals y?
Those came from the original limits. In this particular, I may hold off to that on the specifics of that until I get to the next example, because I think my notes are a little bit easier to read to answer that question on the next example. But basically, when we created it, this particular plane, the yellow one, is coming from the plane y equals x. The blue plane is coming from x equals z, and the top triangle is coming from a z equals fourth root of pi, square root of pi. So the various triangles are all coming from those limits of integration, and that's how I knew what was going on.
Okay.
Does that make sense?
Yeah.
Cool. Good question. What I would like to do is go and start playing with the next. Let me finish up the setup so you're clear what's going on. So, having gone through all of that, we are now able to set up the new limits, the new integral. So same value, the integrand doesn't change at all, but now we're going y, x, z, and we get those limits of 0 to x that we just found, 0 to z, 0 to fourth root of pi. So the integrand's the same, the limits that we find are based on whatever we did with those pictures up above. Can I show this in a different picture? Is that okay?
Yeah, it's okay.
Okay, very good, thank you. Okay. This last question, I think is a valuable one to play with for understanding. So, let's see. So I want to write 5 other iterated integrals that are equal to this quantity. And I believe this one right here is an x squared. It's hard to read in the scan. That's an x squared, and this is a y. So integral from 0 to 1, 0 to x squared, 0 to y of f of x, y, z. And here I've got dz, dy, dx. Okay. So when I say 5 other iterated integrals, here's what I'm referring to. So if you look down, notice all these orders of integration. Z, x, y, x, z, y, z, x. So these are the other 5 possible orders that there could be in this order of integration. Does that make sense? Okay, so the question is, how do you do it? So in this case, what we're going to do to start with is we're going to start by sketching the region. So notice that our z values are going from z equals 0, which would be the xy plane, all the way up to z equals y. So imagine z equals y, so that would be like, you think about it as this line, z equals y. Okay, but it's a plane because since there's no x, that line would then continue like that. So it creates this plane. In R3. So z is going from z equals 0 to z equals y. Then our y's are going from y equals 0. So y equals 0 would be the xz plane to y equals x squared. Oh, we know y equals x squared. Remember y equals x squared, that's our parabola. But there's no z, so we would then extend that curve up like so, to give ourselves kind of this three-dimensional wall, you can imagine. Right? So we have a green plane here. We have a red curvy wall there. And then we also want to let our x's go between 0 and 1. So x equals 0 would be the YZ plane. X equals 1 would be this vertical plane here. Okay. So there's kind of our mashup of all the pictures. And so when we cut away and figure out what's left, what we're left with is just kind of this funky shaped wedge thing here. Okay. Questions about where the shape comes from?
Hey, Dusty.
Hey, Jay.
So have you did the first one? Where did you find z equals to x squared?
I found y equals x squared.
Here, the first from the left.
Oh, here. Good question. Right over here.
Z equals to x squared. Yeah.
Got it. Hold on to that question for a second. Okay, so let me get there in a second. So are there questions about the 3D part of it?
Just like this. Where did you find z equals to x squared?
Okay, that's the only question. Okay, so from here, what I need to do is I can make these projections, and I hope that you can see you can imagine how if we projected this direction, we'd get this shape. The question is, where do those functions come from? If we projected this way, we'd get a triangle, kind of paralleling that triangle. If we projected down, we would get this shape. The y equals x squared should make sense. The z equals y would make sense. The question is the z equals x squared. So remember that what we had was we were given z equals y, and we were given that y was equal to x squared. And so that helps, the combination of these two tells us that z is equal to x squared. Yeah. Questions about the pictures, or ready to put this together? Okay. Let's put it together. So we need to pick an order. It doesn't matter. So pro tip, okay, the easiest order is the one that happens when you leave the middle variable the same. So if we looked at dz, dy, dx, dz, dy, dx, then the inside limits are going to stay the same as 0 to y. But then we need to focus in on which of the three projections. Focus in on, it looks like the xy projection. and we would draw our arrows parallel to the parallel to the y. 1, 2, 3. And so our limits would go from, our y's would be between where and where? Looks like our y's would be between 0 and x squared. Oh, no, I'm doing the same word. I'm doing the same one as before. That's silly. You got to stop me. And then our x's would still be 0 to 1. Let me do the one that I was meaning to do. So if we did dz, dx, dy, so if we did dz, dx, dy, it would, if we do dz, dx, dy, the inner limits will be the same, but then we'll draw our arrows parallel to the x-axis. Come on, red. Parallel to the x-axis. And so our x values are in between, what's the lower limit for the x?
0.
It's coming in right here.
Oh, square root of y.
Square root of y. And our maximum
1.
x would be 1.
1.
And then our y values would be between 0 and 1.
0 and 1.
Okay. This is the easy one because the inside limits are the same. It's more interesting if we pick a different order. So let's pick one order. Somebody make one up. What do you want? What do you want first?
dy dx dz.
dy dx dz. Okay, so I got dy dx dz. So we're going to start on the inside with the y's. Sorry, trying to get my colors. With the y's. And so if I'm looking at the y's, then I want to focus in on the 3D drawing, and I want to draw an arrow that's parallel to the y-axis on the 3D drawing. So you can imagine your arrows coming in. It hits the object there. It goes straight through, and it comes out on the far side. So where did our y's go in, and where did our y's come out? So
In at y equals to 0.
It goes in right here, which would be y equals
E.
Y equals z, yes. Here's that surface, y equals z. And it comes out on the curvy surface on the back side, which would be where y equals x squared, yeah. Okay. So then we're going to do a projection onto the plane that involves x and z, which would be this one right here. And so now we're going to work parallel to the x-axis on that picture. So I draw 3 arrows parallel to the x-axis on this picture. One, at least attempts at parallel. Okay. And so my arrows go in right here on the right side at x equals what?
Square root of z.
Square root of z. And they come out here at x equals
1.
1. Good. And then last but not least, we look at those arrows and we say the lowest arrow is down here when z equals 0, and the highest arrow would be up here when z equals 1. Ooh. Something like that. Does that make sense?
Question.
Go ahead.
So why wouldn't the arrows be, I guess, like going towards z equals x squared? Because some of the arrows would hit along that curve. I don't know. I guess I don't really understand why it's 1.
Are you here?
No, with the z. Draw the z arrows just so I can.
Can you? I think you can annotate and mark what you're looking at.
Oh, okay.
Can you? Does that work? Can you draw on your screen?
Oh, here we go.
So why are we not going that direction?
Yeah.
Because the integrations are always parallel to, we're always running parallel to the axis that we're working with. So, and you always end up with one less dimension. So here with y, we run parallel to the y-axis in our, think about it this way. So we've got 3 variables. So we're doing a 3D drawing, and we're drawing parallel to the y-axis. And then we focus in on the next. We've got 2 variables left. So we have a 2D drawing, and we run parallel to the x-axis. And then we've only got 1 variable left. So we've got a 1D drawing, which would just be the z-axis. And we've got just be the z-axis. And so we'll run kind of along that and say, oh, where could our arrows live? Does that?
Yeah, that makes sense. Thank you.
Good question. Other questions?
Hey, Dusty, can you do one more?
I can. Let me clear all this and just run the same thing, but with a different order. So somebody pick an order.
dy dz dx.
dy dz dx. Okay. So we're going to start on there's 3 variables, so we're going to start on the 3D drawing, and we're going to run, oh, didn't we just do this? Oh, we just reversed this order, right? I think is what we just did. So we're going to still be parallel to the y-axis on the 3D drawing, and so I'm going to come in, boom, 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 enters here, goes through, comes out on the other side. So our y values again are going in at y equals z and coming out at y equals x squared. You'll notice this is the exact same thing we got in the last example. And the reason it's the exact same thing is because we're starting with the same inner variable. It's easiest to answer the question if you do both the ones with the dy's in the middle first, and then do both the ones with the dx's, and then both the ones with the dz's. So that we again need to project onto a 2D surface. We're going to project onto the zx, which is again this same picture. But now we're going to run parallel to the z-axis. And so I'm going to draw 3 arrows parallel to the z-axis. So I've got 1, 2, 3. And so those are going, where are they entering? They're entering at z equals
0.
0. And they're exiting at z equals
X squared.
x squared. And then last but not least, we've only got one variable left, x. So you can imagine taking all of this stuff, squashing it down onto the x-axis. And so all we're doing is we're looking at where did those arrows come from, and like, oh, all of our arrows were living between x equals 1 and x equals 0. Something like that. Is that was fast, but that was another example, and you picked the order for me. Did that help? So one thing I might encourage you to do here is to simply take these pictures and run it in all 5 orders. The number doesn't matter. That's not the point of the question. The point is, can you manipulate it multiple ways? This tends to be a question that I like quite a bit. And so as we wrap up the formal class, I just want to wish you all, bless you all with a good Friday, in the knowledge that our sufferings are momentary, but that the hopes are eternal. So I hope you all have a wonderful weekend. I look forward to hanging out during office hour with some of you that are interested and available. But I look forward to seeing all of you again next week after this beautiful Easter weekend. So have a great day and take care, everyone.